6.4 Part 7 is the application. And so it tells us here that if a system of forces acts on a particle, that particle will move as though it were acted on by a single force equal to the vector sum of the forces. This single force is called the resultant of the system of forces. If the particle does not move, the resultant is 0, and we say that the particle is in equilibrium. So let's look at example 1 here. It says to find the magnitude and the bearing of a resultant R of two forces F1 and F2, where F1 is a 50-pound force acting northward and F2 is a 40-pound force acting eastward. Alright, so first thing I'm going to do is kind of draw this. So we've got two vectors here, two forces. One's going north, one's going east. So if I draw myself a little coordinate plane here, I know I've got this vector that's going north. £50. So we're going to say this is going to be 50. And we got this other vector that's going east. $40. Okay, and so we know that our resultant vector here, or the vector, well, I guess I should say when I put these two together, they're going to have the ordered pair, 40, 50. And so our resultant vector is going to be right here. Alright, so let's talk more about this resultant vector. So it's the two forces F1 and F2. So our resultant vector, so vector R, is equal to F1 plus F2. The two forces added together. So what we can say here then is, what do we know about force 1? Well, force 1 was that 50. Now remember, it's on that y-axis, which is known as our J as well. So we could say that F1 is going to be 50J plus 40 was our F2 down here. And remember, this is the same as our I, So we can say that F2, the force there, is 40I. Now, we always see I written first for all of our activities. So let's switch this real quick. So this is the same as saying 40I plus 50J. And so from there we can find our magnitude, because remember the magnitude of a vector is equal to the square root of the coordinates squared, okay, or the components, So it's going to be 40 squared plus 50 squared. And so we're going to work this out. And so it's at 1600, square root of 1600 plus 2500. And so we find that that's the square root of 4100. And so I'm just going to give an approximation here, okay? So I'm going to take the square root of 4100, and when I round it to the nearest tenth, I get 64.0. So there's my magnitude. So now let's talk about the bearing. Well, first, now remember, bearing is always from the north or from the south, okay? So really in the end, for bearing, we're looking for this angle right here. But we know when we're dealing with vectors that we can find this inside angle theta right here, because we know that tangent of theta is equal to the second coordinate divided by the first coordinate. Now that 50 over 40 is going to give me a quadrant 1 angle, which is where my angle is at. So let's go ahead and let's just take the inverse. So the inverse tangent of 50 over 40. Let's put that in our calculators. And we should get approximately 51.3 degrees. So that means this angle right here is 51.3 degrees. But I need that angle right there. So how are we going to find that? Because that's the angle that's going to give me my bearing. Well, we can take 90, because we know they're complementary, minus that 51.3 degrees, and that's going to give us that little angle there, which is 38.7 degrees. So this little angle is 38.7 degrees. Which means we could write our bearing as 38.7 degrees. We're going towards the east, and it came from the north. Okay? So we can also say here that vector R has a force of, and this is the magnitude, okay, so 64 pounds in the direction of north 38.7 degrees towards the east. And so that is the summary of our answers put together there.